Good morning to all. Welcome to the channel Fidjan. Today we discuss electrostatic potential and capacitance. Second lesson, 12th standard. In this one we discuss a relation between electric field and electric potential. Third video in second lesson. See, in this one first we discuss electric field. Electric field. Electric field means the space around a charged particle. For example, see here, this is the charged particle. Around this charged particle, within which a force is exerted on the another charged particle. That region we call it as electric field. See here, due to this charged particle at point P, a force is acting on this one due to this charged particle. On at point P, one test charge we can place now here, a force is exerted on this one. So on that one, what is the force exerted on test charge? By test charge we call it as electric field or electric field strength. Electric field strength now this point equal to what now? K q by r square. What is the electric field strength at point P or distance from the charge now? K q by r square. What is the electric potential at this point due to this point charge or distance from this is potential at P equal to K q by R. It is the potential and it is the electric field strength at point P due to point charge. Due to point charge. By using this, we can relate an equation and relate what is the relation between electric potential and electric field. We can derive that one. See, for that, what now we have two cases is there. First one, case 1. See, first case what now here we discuss. When electric field is uniform, that case what is the relation between electric field and electric potential? Means when E is uniform, electric field is uniform, electric field is uniform. This case, what is the relation? See, uniform electric field means electric field lines are straight. See, straight lines parallel to each other and equispaced. That electric field we call it as uniform electric field. See here, when electric field is uniform, that case what is the relation between electric field E and electric potential V? This relation we want to find out. For that we can take here uniform electric field. This is the uniform electric field. Uniform electric field means electric field lines are parallel, straight, equispaced. That we call it as uniform electric field. In this uniform electric field, what is the potential at this point to this point? So means first point to second point. What is the potential that we define? For that, what we can do now here, one charged particle. Here we can place Q is the charged particle. It is positive charged particle. Positive charged particle na electric force is acting in the direction of electric field. In the direction of electric field. See here, it is the positive charged particle. Electric field is acting in the direction of electric force is acting in the direction of electric field. That electric force is here QE, charge into electric field. See here, when charged particle placed in the uniform electric field, a force is acting that moves from this point to this point. Automatically what happened here? Their speed is changes. Its speed changes. When speed change now, we can't define the electric potential. So that's why what we can do now here, one external force we are acting here, external force, which is not exactly equal to electric force but approximately equal. So that is here we can write opposite now. So we can write here minus QE. See here, it is the electric force, it is the external force. Because of external force, charge particle is moving without change in speed and without change in kinetic energy. For that purpose, we can apply external force opposite to electric force. Then this charged particle is moving from this point to this point. It takes infinite steps with a constant speed. It moving from this point to this point. Then that case we can define the electric potential. First we here write here what is the electric force acting on this one, external electric force, that is QE. Due to this QE force, charge particle is moving from one point to another point. What is the displacement now here? See, delta R is the displacement from one point to second point, first point to second point. I write here displacement. Displacement is delta R. What is the work done now here? Work done by external force, that is force, external force into displacement, into displacement. See here, external force is what here? Minus QE, and the displacement is delta R. It is the work done by external force. It is the work done by external force. See here, due to this work, charged particle is moving from first point to second point. So charged particle is moving from first point to second point. Some work is done on charge. We call it as electric potential. What is the electric potential here? Where to where moving? First to second. So we can write electric potential V2 minus V1. What is the initial now here? V1. It is final. So means final minus initial V2 minus V1 equal to work done by external force from where to where? First point to second point. On where? On charge. See here, work done by external force is minus QE dot delta R by what is the charge here? Q. Q cancel. What we get now here? V2 minus V1 equal to minus of E dot delta R. V2 minus V1 now change in potential. We can write here delta V. Delta V equal to minus E dot delta R. This is the relation between electric potential and electric field. See, delta V means electric potential, E means electric field. What is the relation now here? Delta V equal to minus of E dot delta R. It is the relation between electric field and electric potential when electric field is uniform case. This one, see, this is, see, first what we can do now? Charged particle here is there, it is moving from first point to second point. Electric force is acting in this one in the direction of electric field. For speed is changes, for not changing speed and kinetic energy, we are applying external force, that is opposite to electric force, that is minus QE. So due to this, what happened here? Displacement delta R. We can write work done by external force into displacement. Force is minus QE, displacement is delta R. See, what is the potential definition? Change in potential means final potential minus initial potential, that equal to work done by external agent moving from first point to second point on charge. See this one, V2 minus V1 equal to W external by charge. W external is what here? Minus QE dot delta or Q. So Q cancel. What we get? V2 minus V1 equal to minus of E dot delta R. V2 minus V1 means delta V minus E dot delta R. This is the a relation between electric potential and electric field when the field is uniform and electric field is uniform. That case, this is the relation. See, based on this, we can do the problem. See, for example, we can take first problem. We can take here charged plates. Here, see, this is positive charged plate, it is a negative charged plate. Yes, now here see, it is A, it is B, difference is here 2 meter. Electric field is positive to negative. See here, this is the electric field direction. What is the electric field now here? 10 Newton per coulomb is the electric field. So find the potential. Find electric potential. Electric potential at point B, at plate B, at B, we want to find out. For that, what we can do now here? We can use delta V equal to what? Minus of E dot delta R. Delta V means final potential minus initial potential. This initial potential is 20 volt. We want to find out B. So final is what? VB. VB minus VA equal to what now? Minus E dot delta R. E means what here? 10 Newton per coulomb. Yes, na? Into delta R, 2 meters. We can write here 2. What we get now here? See, VB minus VA equal to minus 20 volt. See, VA we have. So what now? 20. So VB minus 20 equal to minus 20 volt. VB equal to minus 20 volt plus 20 volt. What now we get? 0 volt. What is the potential at B? Equal to na 0 volt. What is the potential at plate B na? 0 volt. This is the solution C by using this relation. It is uniform electric field. So we can use this relation. Delta V equal to minus E dot delta R. Delta V means VB minus VA. E means 10. Delta R means 2 meter. So just we can write, we get the potential at B. Yes na? See, next problem, second one. I write here second problem. So what na second problem here? See, this is the uniform electric field E. See, this is the uniform electric field. Here, see, this is the square. Its length is 1 meter. Its length is 1 meter. It is A point, B point, C point, D point. What we find out now here? Potential. Find electric potential. Find electric potential. First point, see, VB minus VA we want to find out. Second one, see, second one is VD minus VC, VD minus VC. Third one, what we find out now here? VA minus VD, VA minus VD. Fourth one, VC minus VA we want to find out. VC minus VA we want to find out. See, these four we can do. For that now here see, we use, it is uniform electric field na, so we use uniform electric field. When uniform electric field is there, what is the relation between electric field and electric potential? Uniform electric field na, here what is the uniform electric field na, here 20 volt per meter. Electric field equal to what? 20 volt per meter. So in this case, what is the relation na? Delta V equal to minus E dot delta R. Delta V means here what we want, VB minus VA. VB minus VA, it is final minus initial this one. See, final this one, initial means here to here charged particle is moving, means minus E dot delta R means E delta R cos theta. Both are in same direction, displacement and force both are same direction, so we can take cos 0. See what we get now here, see, E is what? 20 into delta R is 1 meter, cos 0 1. So what now here? Minus 20 volt. See, B is electric field at B is, this is the direction of electric field. Potential at A is less, greater than B. Why? Because electric potential is always decreases in the direction of electric field. It is the first point. More potential. Here less potential. So B is less than A. So we can write B now first here. So minimum minus maximum now we can get negative. So what is the potential here? 20 volt. So delta V, VB minus VA, magnitude now here we can write 20 volt. What is the magnitude of VB minus VA na? 20 volt. See, this is the first one solution. See second one. What is the second one now? VD minus VC. VD minus VC. So VD minus VC na minus E delta R cos theta. Here see, VD, this is the final point, it is the initial. So means this is the field direction, it is the displacement. So both are in opposite direction. So we can write minus 20 into 1 into cos 180. Cos 180 means minus 1. See here what we get, minus of minus plus 20 volt we get. See, VD minus VC, what na? Plus 20 volt, or otherwise we can see here, it is the potential is more here, here potential is less. What we can write? VD minus VC, D is greater than C, so that's why positive potential. So we can write magnitude only na, 20 volt we can write it. So VD minus VC equal to 20 volt. Third one you see here, third one, VA minus VD, VA minus VD, VA minus VD equal to minus of E dot delta R na, E delta R cos theta. Here cos theta is, see, this is the electric field, it is the potential, both are perpendicular. So what we can write? VA minus VD equal to minus E delta R cos 90. Cos 90, 0. This total term 0. VA minus VD equal to potential is 0 volt. What is the potential in VA to VD na? 0 volt. See fourth one. See here VC minus VA. VC minus VA equal to minus E delta or cos, here see VC minus VA, angle is, this is the electric field, electric field is this one, and angle is 45 degrees with the electric field. See it means this is the electric field, it is 1, so means 45 degrees, cos 45. So cot 45 now here see minus E 20 delta R is 1, cos 45 now 1 by root 2. See here, so means this we can write it as 10 into 2, 2 means root 2 into root 2 we can write into 1 by root 2. So root 2 cancel, what we get now, minus 10 root 2 volt, Vc minus Vd. So means C is less than A. So that's why here we can get minus 10 root 2. Minus 10 root 2. C is the minimum potential, A is the maximum potential. So along the electric field, potential is decreases. That's why here less potential, here high potential. First C is there. Minimum minus maximum na we get negative. So this is the electric potential. By using electric field and electric potential relation, we can find the electric potential. So in this case, next the third one, you see here electric field, this is the electric field. See electric field, here electric field is 10 volt per meter, 10 volt per meter. Here see triangular shape is there, here see this one, see here it is A point, B point, C point. What we find out now, here first one VA minus VB we find out, and second one see here VC minus VB we find out. See first we can find out VA minus VB, so means minus E delta R cos theta. Here see VA minus VB, what is the angle now, here 60, this is the electric field, it is the potential. So what is the electric displacement, what is the here, theta is 60, so minus E, E means 10 into delta R is this distance is 2 meter. See 2 into cos 60, cos 60 now 1 by 2, minus 10 into 2 into 1 by 2, 2 2 cancel, means minus 10 volt. See here A is the less potential, B is minus more potential. Why? Because B point is before is there, A is later. So electric field in the direction of electric field, electric potential decreases, that's why it is maximum, it is minimum. So A is first is there, that's why we can write VA minus VB equal to minus 10 volt, magnitude na 10 volt only. Yes na. See the second one, what is second one, VC minus VB, VC minus VB. See here it is the electric field direction, displacement this direction. What we can write here, minus E delta R cos 180. Cos 180 means minus 1, so already minus is there, plus E is 10, delta R is 2, so means what we here we can write 20 volt. See VC minus VB, see VC minus VB, this is the electric field direction, is the displacement. Yes, now VC minus VB, this is final, it is initial, so same direction, not 180, so 0 only. See here, here to here moving, this is the direction of electric field and displacement, so cos 0, so minus we get minus 20. Why now here C, less potential, maximum potential, so less minus maximum minus, so we can get 20 volt, but magnitude is VC minus VB equal to 20 volt, magnitude is 20 volts. These are the problems belongs to electric field and electric potential relation by using relation in uniform electric field, uniform electric field. Second case we discuss, when the field electric field is non-uniform, what is the relation between electric field and electric potential? See second case, case 2 we can write here. What is case 2 now, here see when electric field is, electric field is non-uniform, 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 that case what is the relation between electric field and electric potential? What is the relation between electric field and electric potential? That we can derive an equation. See, this is also very important. So many times they asked from this problem in board exam also, not only NEET exam. So board exam also asked based on this year also to 2025 paper also they asked one question. See, for that first we discuss what is the relation between electric field and electric potential when electric field is non-uniform. So non-uniform now it is the uniform non-uniform electric field. See here, see, like this is there. So where closer now electric field is more, far na electric field less, means non-uniform. So electric field is maximum, minimum, maximum, like this is there. So in this case we can select 2 points. This is the first point, this is the second point I select. See, this is first point, it is the second point. See here, charged particle is moving from here to here, non-uniform now. So that's why we can select small region. See, we can select here this part, this part. In this part, this is dr, length is dr, displacement is very very small. This case definitely field is uniform. Why? Because very small na elemental region. So that's why. See, we can write here for this region what is the potential now here, dv, that equal to minus e dot dr. Yes na. See, electric field is uniform at a small region. So that region is here dr. What is the electric potential? dv, that equal to minus e dr. See, this region we can say next, next, here next. See, this how many is there? Infinite parts is there. So infinite part is there. We can use integral. All we can add na. We get integration. What is the potential between 1 to 2? So that we can write for that V2 minus V1 total potential. What we can write now? We can take integration. Why? Because now this potential, this potential, this potential, all potential we can add. We can take integral E dot dr. This position vector is r1. This position vector is r2. So means what is the interval now here? R1 minus R1 to R2. Position vector is R1 to R2. See, V2 minus V1 means delta V. Delta V equal to minus of integral R1 to R2 E dot delta R. It is used to find, it is used and find the electric potential in non-uniform electric field. Non-uniform electric field. See, delta V equal to minus of R1 R2 integral minus of R1 R2 E dot dr. See, here we have three relations is there for electric potential and electric field. First one, delta V equal to minus E dot delta R, one relation. dV equal to minus E dot dr we can write, and delta V equal to minus of integral R1 to R2 E dot dr. This is another relation. See, first one, second one, third one. These three relations are important. See, first one is what? Delta V equal to minus of E dot delta R. It is in uniform electric field. These two are non-uniform electric field. dV equal to minus of E dot dr, or delta V equal to minus of integral R1 to R2 E dot dr. See here, in this one we can take a Cartesian electric field. So Cartesian electric field now how to write now here? See, E equal to Ex I cap plus Ey j cap plus Ez k cap is the Cartesian electric field. So position vector now R equal to x I cap plus y j cap plus z k cap. It is the position vector. Here differentiate now dr equal to dx I cap plus dy j cap plus dz k cap. See what now here we have? See, dv equal to what is the relation? Minus E dot dr. So E means here this one. See, Cartesian form. So means Ex I cap plus Ey j cap plus Ez k cap dot dr means this one, dx I cap plus dy j cap plus dz k cap. See here this dot product. So dot product na I dot I equal to 1, j dot j 1, k dot k equal to 1. So we can use here dot product means ex I dot I only we can take, j dot j k dot k, remaining terms 0. That's why we can write here minus ex dx minus ey dy minus ez dz. This is dv. dv equal to what we are getting? This is the dv. See here we can do partial differentiation. This total equation what we are getting, dv equal to minus of ex dx minus of ey dy minus of ez dz. This we can do now here partial differentiation with respect to x. Means for example here see partial differentiation with respect to x, that meaning y comma z are constant, y comma z are constant, their differentiation dy equal to 0, dz equal to 0. Partial differentiation means with respect to what we are doing, that only doing, remaining terms will be constant. With respect to x means y z is constant, with respect to y means x and z are constant, with respect to z means x and y are constant, means dy dx is 0 that time, like that. See for partial differentiation with respect to x, this one, so what we can write now here, see dou v by dou x with respect to x na, dou v by dou x. For partial differentiation we can use dou d na full, so partial na we can write dou v by dou x, that equal to minus of ex dou x by x, dou x by dou x, dou x cancel, remaining terms 0. Why? Because here no x, here no means dy na 0, dz na 0, that's why. See here we can get dou v by dou x equal to minus ex. See again I write, this is the actual equation, dv equal to minus ex dx minus ey dy minus ez dz. It's we can differentiate partially differentiation with respect to x. With respect to x means y and z are constant. Y and z are constant means their differentiation dy equal to 0, dz equal to 0. This case we can differentiate this one with respect to x, means dou v by dou x minus ex, dou x na dou x by dou x, dou x cancel, so what we get ex, remaining term this and this term 0, so what we get dou v by dou x equal to minus of ex. From this what we can write, ex equal to minus dou v by dou x we can write. We get after partial differentiation with respect to x, we get ex equal to minus dou v by dou x. Similarly ey equal to what we get na, minus dou v by dou y, and similarly ez equal to minus dou v by dou z. These are the three terms we are getting after partial differentiation. With respect to x na, ex equal to minus dou v by dou x, y na minus dou v by dou y, z na minus dou v by dou z. See here actually what we have, electric field E equal to Ex I cap, Ey j cap, Ez k cap. Instead of this we can write electric field in Cartesian form. See, instead of Ex we can write this one, dou V by dou x I cap minus dou V by dou y j cap minus dou V by dou z k cap. It is the electric field. For finding electric field we can use, this is the formula we can use. Yes na? For dv equal to minus e dot delta, or dr delta v equal to minus of integral r1 to r2 e delta dr, or we can use electric field na, this is the formula, minus dou v by dou x I cap minus dou v by dou y j cap minus dou v by dou z k cap. This we can use and find the electric field. When the potential they will give na, we can use this one and find out. Yes na? Understood na this one? See again once, Cartesian form, ex I cap, ey j cap, ez k cap, radius vector xi cap, yj cap, zk cap, differentiation dr dxi dy dyj dz k, product dv equal to what, minus e dot dr na, E means EXI, EY, J, EZK. DR na this one DXA, DYJ, DZK. So dot product I dot I, J dot Z, K dot K1. So that only we can take remaining term 0. That's why dV equal to minus EX dx, EY dy, EZ dx. This is partial differentiation with respect to x. Means y and z constant, dy equal to 0, dz equal to 0. With respect to x means C. Dou v by dou x minus Ex dx na dou x by dou x cancel. What we get? Dou v by dou x equal to minus Ex. Y now here remaining term 0. So Ex equal to dou v by minus dou v by dou x. Similarly, Ey equal to dou v by dou y. Ez equal to dou by dou y. We can apply here. We get electric field formula. What is the electric field formula na? E equal to minus of dou v by dou x I cap minus of dou v by dou y j cap minus of dou v by dou z k cap. It is the formula for finding electric field when potential is given. Yes, na? This is the case 2. When the field is non-uniform, that case we have main formula is this one and this one. See dV equal to what? Minus E dot dr. Delta V equal to total potential from first point to second point. Means V2 minus V1 equal to integral minus of integral R1 to R2 E dot dr. E dot dr. These formulas we can use and solve the problem. This is the case 2 when electric field is in non-uniform. Non-uniform. Now see here, we can solve the problem. First one, see what they give now here. Potential they give. Potential is what now here? X 2x minus y plus z. 2x minus y plus z and find electric field at 1 comma 0 comma 1 and magnitude of electric field also we want to find out. See here potential they give, we want to find out electric field. For that what we can use now? First formula dV equal to minus of E dot dr we can use. Dr what we can use now here? See dV E na sorry dV equal to E dot dr we can use. Here what we can use now? This is the formula we can use, not that one. Electric field equal to what? Minus of dou v by dou x I cap minus of dou v by dou y j cap minus of dou v by dou z k cap, not this one. Yes na? Sorry. So we can use that one. So electric field formula what now here? Minus of dou v by dou x I cap minus of dou v by dou y j cap minus of dou v by dou z k cap. So first we can write dou v by dou x we can find out. What is the dou v by dou x here? X here only is there, remaining z y z is there 0. So 2x differentiation na 2. Next dou v by dou y we can write dou v by dou y. Here only one term is there. So what we can write? Minus 1. Dou v by dou z. See only this one is there, remaining 0. So that's why here differentiation na 1. So just we can substitute here. What na? This minus common and out na. So we can write electric field equal to what is the dou v by dou x? 2. 2 I cap. We can write yes minus 1 j cap minus sorry plus 1 k cap. Here what values we are getting, that one we can write. Why not? Here minus all is there, common and send out. So we can write 2 I cap minus 1 j cap 1 k cap. Yes na? This is the electric field due to this potential. So what now? Magnitude of electric field. What now here? 2 square plus 1 square plus 1 square. See root of minus 1 whole square. So what we get here? 4 plus 1 plus 1. 4 plus 1 5 plus 1 root to 6. It is the magnitude of electric field. This is the potential electric field. We find out 1 comma 0 comma 1. Here we are not using points. Why? Because here all we are getting constant only, no variable. So no need to substitute. Directly we can write that values. Yes na? Second one, see when the potential is, second problem, see potential is V equal to x square y minus plus y square z. What now here? Electric field we want to find out. Electric field at 1 comma 1 comma 1, and magnitude of electric field also we find out. Magnitude of electric field. For that, what is the formula? Now here see, electric field equal to minus of dou v by dou x I cap minus of dou v by dou y j cap minus of dou v by dou z k cap. First we can write dou v by dou x. What now here dou v by dou x? So this one with respect to x we can do. Here x is there, here no x. Yes na? We can write here differentiation 2xy. What is the point here? 1 comma 1 comma 1. So at 1 comma 1 comma 1 means where x value 1, y value 1. So means 2 into 1 into 1. So that equal to here we get 2. So dou v by dou y. Here see dou v by dou y. Here two terms is there. Y here is there, here is there. Both we can differentiate. Here differentiate na y. So means x square only we get. Plus here y is there, so 2yz, 2yz, just we can substitute the point 1 comma 1 comma 1, x value 1, y value 1, z value 1, so 1 square plus 2 into 1 into 1, so 2 plus 1, so 3. Here dou v by dou y is 3, dou v by dou z na see 1 comma 1 comma 1, here z is here is there, here no z, so we can write y square only, z differentiation 1, so y square only, so y square means here 1 square, so means 1 we get. So dou v by dou x is 2, dou v by dou y is 3, dou v by dou z is 1, just we can substitute here. See electric field equal to minus, no need to write right now, common and send out, so what we get here 2 I cap dou v by dou y na 3 plus 3 j cap dou v by dou z na 1, so 1 k cap, 1 k cap. This is the electric field. So magnitude we want na, see here root of 2 square plus 3 square plus 1 square. 2 square means 4, 3 square means 9, 1. So what we get now here, electric field equal to 4 plus 1, 5 plus 9, so 14. Root 14 is the electric magnitude of electric field is root 14. Electric field is 2 I cap, 3 j cap plus 1 k cap. Yes na? See third one. Here see V is x square y square z and z square x. This is the V. We want to find out electric field and magnitude also find out. Same formula here. See, but here term is different. So potential is what? X square y plus y square z plus z square x. See here, first we can write dou v by dou x, means x where is there, here is there, here is there, 2 we can take it, x square means 2xy plus here z square only, y na x differentiation 1, so z square only we have, so we can write here 2 into point is 1 comma 0 comma 1, so y value 0, here this term totally 0, 1 into 0 plus x z value 1, so 1, so we get 1. Next dou v by dou y, so here see, here y is there, here y is there, means what we get here, x square, this differentiation 1, so this one 2yz we get. Why? Because y square differentiation 2y, z like that only. See x value 1 comma 0 comma 1. So y value here 0, here 1 only is there. So means 1 square plus 2 into 0 into 1. So means 1 only we get. See dou v by dou z. It's not dou v by dou z. Here z is there, here also z is there. So here z means y square we get, here z means 2y, sorry, 2xz we get. This term 0, this term 2 into 1 into 1. So what we get? 2. Yes na? Now see, we can substitute here electric field equal to electric field vector. See dou v by dou x 1. So 1 I cap plus dou v by dou y 1, 1 j cap plus dou v by dou z 2, 2 k cap. It is the electric field. Yes na? we want magnitude of electric field. So means see 1 square plus 1 square plus 2 square. What we get now here? Root 6. This is the magnitude of electric field. So this is the third problem. Yes, na? Third one. See, now we can find potential, but they gave electric field. So that we can use electric field they gave, we find the electric potential. See, this is different somewhat here. See, I read here problem, fourth one, electric field equal to here. What is the electric field now here? See, x I cap minus 2y j cap and z k cap. What is the interval now here? See where to where now here? 0 comma 2 comma 4 to 2 comma 1 comma 0. Find electric potential. Find electric potential we find out. For that, see here what formula we can use now. See delta V equal to minus of integral R1 to R2 E dot dr we can use. E dot dr. E means this one. Dr means dxi, dyj, dzk na, that we can use. Here see R1 to R2 means this is the point xx 02, yy 21, zz 4 comma 1. We can write here delta V equal to minus integral R1 to R2. E means this one x I cap minus 2y j cap plus z k cap into dr means dx I cap plus dy j cap plus dz k cap. Yes na? Here see I dot I 1 j dot j 1 k dot k 1. So we can write here x dx. I write here minus integral x dx. Yes na? This minus I remove. See why na? See total will come na, that's why you can write outside. See why I can write x dx. Next minus integral 2y dy plus integral z dz. What is the interval na? X coordinates 0 comma 2, 2 comma 1, 4 comma 0. Here what we can write 0 comma 2. Here 2 comma 1, here 4 comma 0. Yes na? So x dx na x square by 2. What is the interval here? 0 comma 2. This one minus 2y square by 2. Interval is 2 comma 1. Here z square by 2. What now here? 4 comma 0. 4 comma 0. See 2 comma 0 comma 2, 2 comma 1, 4 comma 0. See here this one upper limit we can write here 2 square means 4, 4 by 2. Lower limit not 0, total value 0. Next this one minus of 2 2 cancel, y square means 1 square 1 minus 2 square means 4. Next plus see upper limit 0 minus na here minus 4 square 16 by 2. Yes na? See here minus is there minus 3 minus here 2 ones 2. See minus 3 minus plus 3 will come here 2 plus 5 minus 8 means minus 3. What is the value now here? Delta V equal to minus 3 we get. Yes na? This is the solution this one. See what we can do now here electric field they give points they give, we can use dv delta v equal to minus of integral r1 to r2 e dot dr. E means xi cap minus 2yj cap plus zk cap. Dr means dxi dyj dzk, just a dot product. What na? I dot I, j dot j, k dot k we have remaining term 0. So x dx, y dx, dy, z dx. Intervals is x coordinates for this, y coordinates for this, z coordinates for this. So we can use and simplify. See next one. So in this year 2025 in board exam they ask this is the problem. See So by based on this one only, relation between electric field and electric potential, by using that formula we can find the that one. See what is the problem now here. See, electric field in a region is given by, see I write the problem here, electric field, electric field in region is given by, in region given by, what is the electric field now, E equal to 40 xi cap Newton per coulomb. This is the electric field they given. What we have to find now here, to calculate work done by, work done, to calculate work done to move unit positive charge, unit positive charge from 0 comma 3 meters to 5 meters to 0. Oh, this is the problem. This year board exam problem, this one. Electric field in a region given by E equal to 40 xi cap Newton per coulomb, to calculate work done to move unit positive charge from 0 comma 3 meters to 5 meter comma 0. See, for that now what we can do now here, see, electric field they give, potential we find out first. See, for potential what formula, delta V equal to minus of integral R1 to R2 E dot delta dr, E dot dr. E here only x coordinate they give, so we can write here minus E R1 to R2. E means here 40 x I cap, so we can use here dx I cap only, dy j cap dz k cap, that and all 0. Why not, j k is not here, that's why what we get here minus integral R1 to R2 x dot x naught I dot I naught 1, so means 40 x dx we get. What is the interval here, x coordinates only we want here, 0 to 5 only, y coordinate no, z coordinate no, only x coordinate. So we can write R1 to R2 means here minus, R1 means here 0, R2 means 5, what, 40 x dx, 40 x dx means minus 40 x square by 2, what is the interval now here, 0 to 5, 0 to 5. So we can write here minus 40 x square na 25 by 2, minus 0 means 0 we get. So that's why here 20 into 25 minus 500 volt. What is the potential now here? Minus 500 volt. So means magnitude now here, magnitude equal to 500 volt. What is the potential now? 500 volts. What we want to do here, calculate the work done. So actually potential equal to what, work done by charge, work done equal to potential into charge. So potential we know, what is the potential, 500, charge na unit positive charge 1 coulomb, so means 500 into 1 coulomb, here volt per coulomb, sorry, Newton per coulomb. So what we get here, work done equal to 500 joules. What is the work done in moving unit positive charge from 0 comma 3 meters to 5 meter comma 0 na, 500 joules. This is the problem given in this year 2025 CBSE board exam. Yes na, this is the problem. Yes na, see same type of problem one more we can do. What na that one, see here, this is the last problem in this concept. See what's the problem now, electric field, same here, electric field in a region is given by 40 xi cap. Now here instead of 40 I cap, what now we can write here, 10x plus 4, 10x plus 4 I cap Newton per coulomb. And to calculate the work done to move unit positive charge from, here we they give, see 5 comma 0 to here 10 comma 5 meters, 10 comma 5 meters, same problem, same method. See we can change here, see this only changed. Now see here delta V, equal to minus of integral r1 to r2. E means here 10x plus 4 I cap. Here dr means dx I cap, dy j cap, dz k cap. Here only one is there, so we can write dx I cap only I write. Yes na, I dot I 1. So we can get, so minus of integral r1 to r2 10x plus 4 dx we get. What is the interval now? Here x coordinate only. See here x coordinate is 5, here 10. So 5 to 10 only we can take here. 5 to 10. See what we get here, minus 10x difference integration x square by 2 plus 4 integration 4x. This is the 10x square by 2 plus 4x. This integration means integral 10x x square by 2 integral 4 dx na 4x. What is the interval? 5 to 10. Just we can substitute, we get the value. See here, delta V means change in potential equal to minus upper limit we can write. So means 10 into 10 square by 2. So means 2 ones 2 fives. Next plus 4 into 5. Yes na, this over. Next minus of up lower limit, minus of 10 into 5 square by 2. Yes na, 5 square by 2. See here 2 ones 2 fives plus 4 into 5, this one. See this is the one. See here minus, here see 10 square na 100 into 5, 500 plus 4 5 jar, sorry 10 na, here 10 jar 40. Yes na, see here minus 5 square 25 into 5 125 plus 20. Yes na, see minus 540 minus 145. So what we get now here, minus 540 minus 145, 395 we get. 395 we can take delta with this one, magnitude we can take na 395. What we want to find out here, work done to move unit positive charge from 5 comma 0 to 10 comma 5. Work done means potential into charge. Potential is what here, 395, charge is 1. So what we get, 395 joules. What is the work done to move unit positive charge from 5 comma 0 to 10 comma 5 na, 395 joules. So this is the concept relation between electric field and electric potential. Please watch this video, like and subscribe and share the video. Thank you.